What is knowledge representation? Knowledge representation is a sub-area of artificial intelligence or AI that is concerned with understanding, designing, and implementing ways of representing information in computers so that programs or agents can use this information to derive information that is implied by it, to converse with people in natural languages, to decide what to do next, to plan future activities, to solve problems in areas that require human expertise. So, knowledge representation bridges the gap between human and computer by storing information in appropriate manner in a computer system so that this information can be reused in a suitable way at a later point of time. The program or agent can use this information to derive information that is implied by it, that is, to deduce information that is valid if that specific information is valid. The agent can also use that information to converse with people in natural languages. Many NLP or natural language processing programs make use of the inherent syntax of information saved in a system so that it can produce output in human recognizable fashion, in essence, talking to the human. The agent can also use the saved information from a knowledge representation to plan future activities, which might be as easy as planning a scheduled backup for a database or as complex as deciding the turning of an AI powered car on the next turn on the road. The agent can also use the information in the knowledge base to solve problems that require human expertise, which implies solving a typical problem that requires human intervention. For example, in the game of chess, there might be a search instance at a particular point of time that requires a know about of that situation beforehand. In such cases, if the information in the knowledge base is correct, the agent can take the necessary action that would only be otherwise possible by a human having expertise for handling that situation. So, representing knowledge is a critical part of implementing AI modules. We should choose the data structure used to store and specify the information in a proper way before actually implementing it. Intelligent agents should have the capacity for perceiving, that is, acquiring information from environment, knowledge representation, that is, representing its understanding of the world, reasoning, that is, inferring the implications of what it knows and of the choices it has, and acting, that is, choosing what it wants to do and carry it out. So, what is meant by these statements is that for an agent to be functional in an AI environment, it must have the properties of perceiving, knowledge representation, reasoning, and acting. Perceiving means it is able to understand and interact with its environment. Knowledge representation means it is saving the state of the environment and other properties related to it in a proper format. Reasoning is a new term here, and in simple terms, it means that given a knowledge base, the agent can deduce other information by applying certain operations aloud. For example, in the case of the AI powered vacuum cleaner, given the amount of dirt on the surface, if the vacuum cleaner adjusts its power of the rotor, then it is reasoning well. Finally, acting implies that the agent is able to carry out what it is supposed to be doing. Representation of knowledge and the reasoning process are central to the entire field of artificial intelligence, since without representing the knowledge, the computer will not be able to understand the context or possibly any part of the problem that it is meant to solve. Formally, the primary component of a knowledge base agent is its knowledge base. A knowledge base is a set of sentences where sentences represent some assertions about the world that are known to be true. Each sentence is expressed in a language called the knowledge representation language. A knowledge representation language can be as simple as a Boolean equation or as complex as a JSON files or an XML structure. So if we have proper knowledge representation language syntax, we can represent the knowledge for the AI problem in our knowledge base, and our agent can use the same to perform its actions by reasoning on it alongside with perceiving the environment. Now we shall understand the term reasoning in context to AI. Deriving information that is implied by the information already present is a form of reasoning. As I have told earlier, if the agent can deduce other information than already present in the knowledge base, it is known as reasoning on the part of the agent. Knowledge representation schemes are useless without the ability to reason with them. So it is called knowledge representation and reasoning, or KRR. What is conveyed by this sentence is that without reasoning, there is no need to store the knowledge as a representation in a computer system. Otherwise, there would be no result from the procedure of storing information in that particular syntax if one cannot reason from it, thereby making the knowledge base redundant. So the two terms of knowledge representation and reasoning are clubbed together to knowledge representation and reasoning, or KRR. Sentences represent some assertions about the world. There must be mechanisms to derive new sentences from old ones. This process is known as inferencing or reasoning. Inference must obey the primary requirement that the new sentences should follow logically from the previous ones. So, as I have already stated, reasoning is deducing new information from already present information in the knowledge base. The terms reasoning is also known as inferencing, and the primary rule for it is that new information should follow logically from the already existing information in the knowledge base. Now we move on to types of methods of implementing knowledge representation. There are many ways of representing knowledge using different methods. In symbolic, it could be declarative language, imperative language, and hybrid language, and in non-symbolic way, it could be neural networks and genetic algorithms. So there are two ways to go about implementing knowledge representation: symbolic or non-symbolic. Symbolic AI refers to the fact that all steps are based on symbolic human readable representations of the problem that use logic and search to solve that particular problem. So symbolic AI thus implies that there are specific rules, logic and search patterns and syntax to represent and reason with the information of the system. On the other hand, in non-symbolic methodology, there is no one specific syntax for knowledge representation. Instead, they perform calculations according to some known principles that have demonstrated to solve problems typically by mimicking a human brain. They perform those calculations directly on the input, thereby removing the need to store the knowledge in a particular syntax. Examples of symbolic method is using declarative language or imperative language, whereas examples of non-symbolic methodology are using genetic algorithm or deep learning in an AI system. Key advantage of symbolic AI is that the reasoning process can be easily understood. A symbolic AI program can easily explain why a certain conclusion is reached and what the reasoning steps had been. It means that we know what steps the agent has taken to produce the output it shows. This is often not the case in non-symbolic methods, as we will see next. Non-symbolic AI systems do not manipulate a symbolic representation to find solutions to problems. Instead, they perform calculations according to some principles that have demonstrated to be able to solve problems, without exactly understanding how to arrive at the solution. Examples of non-symbolic AI include genetic algorithms, neural networks, and deep learning. The origins of non-symbolic AI come from the attempt to mimic a human brain and its complex network of interconnected neurons. Non-symbolic AI is also known as connectionist AI, and the current applications are based on this approach, from Google's automatic transition system that looks for patterns to IBM's Watson, Facebook's face recognition algorithm to self-driving car technology, etc. A key disadvantage of non-symbolic AI is that it is difficult to understand how the system came to a conclusion. This is particularly important when applied to critical applications such as self-driving cars, medical diagnosis, among others. Examples of non-symbolic AI systems are those that employ deep learning, and there are several layers in a deep learning network, and to produce the deduction of the final output from the network is very cumbersome task. A key disadvantage of symbolic AI is that for learning process, the rules and knowledge has to be hand coded in the program, which is a hard problem. So in a symbolic AI system, we have to mention each and every rule as hard coded with the agent so that it can correlate with the knowledge base and act. A drawback of non-symbolic system, on the other hand, is that such non-symbolic systems such as deep learning powered applications cannot take high risk decisions. So this slide gives examples of symbolic and non-symbolic methods. Symbolic methods might be declarative languages such as logic, or imperative languages such as C, C++, Java, etc., or hybrid languages such as Prolog, or set of rules, frames, or semantic networks, whereas non-symbolic methods can be neural networks and genetic algorithms and so on. Now we shall move on to the topic of types of knowledge. Knowledge can be descriptive or procedural. In descriptive knowledge, we are given description of notions, facts, and rules of the world. No information about the procedure of or target which are required to achieve is given. Example is, for each lecture there is a specific time and place, or only one lecture can take place at each time and place. This is descriptive language as these are just raw facts. Descriptive knowledge is non-procedural and independent of targets and problem solving as it is based on facts. In descriptive knowledge, we are given only raw facts or truth statements, and following it is easy for a computer. We can also say declarative knowledge is knowing about something which can be expressed in declarative sentences and consists of facts. Example is, the first step in cooking a vegetable is chopping it. To prepare a dish, one needs to gather its ingredients. In procedural knowledge, on the other hand, description of procedures required to achieve targets is given instead of facts. Knowledge of the order in which actions must be performed or heuristic knowledge is also given. Example, to know which lecture hall should be occupied by a trainer, first create the list of lectures to be conducted, or to reach Athens faster, you should take an airplane. Procedural language or procedural knowledge, also known as imperative knowledge, is about rules, strategies, agendas, procedures. It is mainly knowing how to do something and can be directly applied to a task. Procedural knowledge depends upon the task on which it is applied. Example, how to cook vegetable or how to prepare a particular dish is procedural knowledge. Now we will see what are logical agents. Humans can know things and reason. Similarly, representation is how things are stored, and reasoning is how the knowledge is used to solve a problem or to generate more knowledge. So, logical agents are AI powered programs that reason and represent information. Knowledge and reasoning are important to artificial agents because they enable successful behavior difficult to achieve otherwise, which is specifically useful in partially observable environments. Logic is the primary vehicle for representing and reasoning about knowledge. The main advantage of using formal logic as the language of AI is that it is precise and definite. This allows programs to be written which are declarative. They describe what is true and not how to solve a problem. This allows for automated reasoning techniques for general purpose inferencing. Now we discuss about knowledge-based agents. Central component of a knowledge-based agent is a knowledge base. Knowledge base is nothing but a set of sentences in a formal language. Sentences are expressed using a knowledge representation language, and there are two generic functions that pertain to each knowledge-based agent. First one is tell, that adds a new sentence or facts to the knowledge base. Second one is ask, which which is used to query what is known from a knowledge base, and that can be done by user. So a knowledge base agent includes a knowledge base and an inference system. A knowledge base is a set of representation of facts of the world as we have discussed earlier. Each individual information is called a sentence. The sentences are expressed in a knowledge representation language. In this slide, we see what the AI agent must be capable of. The AI agent must be able to represent states and actions, that is, represent knowledge in the system, incorporate new percepts, that is, maintain the knowledge base properly by updating when necessary the percepts that are maintained in the knowledge base, update internal representations of the world, that is, update the environment percepts as required, reduce hidden properties of the world, that is, reduce unknown facts from the facts that are already there in the knowledge base, reduce appropriate actions, that is, take appropriate actions based on those facts. On the right hand side, we can see a diagram which clearly states that knowledge base should be domain specific and the inference engine should have domain independent algorithms. This allows the AI system to operate independently of the knowledge base. Knowledge based agents, the algorithm. Here we see a function with the name KB agent which takes a percept as an argument or input and returns an action. It has the KB or knowledge base as the data part that is static, that implies that it is stored permanently, and optionally a counter T is maintained that saves the runtime of the agent. First statement in the function is tell, which passes as arguments the knowledge base and the percept sentence base out of the percept from the original parameter. The runtime is also passed as reference to this tell function. The tell function, when executed, updates the KB with the percept sentence or percept parameter and updates the time taken in parameter t. The next statement assigns variable action with the output of ask function that has two parameters passed to it, the knowledge base and an action query which is invoked implicitly using the make action query function that makes an action sequence based on situation and updates parameter t with time taken. Finally, the tell function is again invoked, this time with the action sequence that is formed by the action variable developed above, so that new information is updated in the knowledge base. Finally, the runtime of the algorithm is incremented by 1 and the action is returned. In summary, knowledge-based agents are best understood as agents that know about their world and reason about their courses of action. Tell and ask interface are operations for adding new sentences to the knowledge base and querying what is known, respectively. This is similar to updating and querying in databases. The inference mechanism is a mechanism for determining what follows from what has been told to the knowledge base. So inference mechanism basically infers from whatever is there already in the knowledge base, and the ask operation utilizes this inferences mechanism to produce more query results. So in this slide we'll be discussing the knowledge base agent types of declarative and procedural cases. In declarative case, we can build a knowledge base agent simply by telling it what it needs to know, and in procedural case we can encode desired behaviors directly as program code, and minimizing the role of explicit representation and reasoning can result in a much more efficient system. So it wants to say that when we minimize the role of explicit representation and reasoning while implementing a procedural case of AI, then it can result in a much more efficient system. Now we will discuss propositional logic. Propositional logic is concerned with the truth or falsehood of statements. If proposition symbols P1 and P2 are sentences, then we have the not operator, which is shown by this small operator here. So if S1 is a sentence, then not of S1 is a sentence. That is termed as negation operation. And then we have the AND operator. If S1 and S2 are sentences, then S1 and S2 is a sentence. This is the conjunction operation. Next we have the OR operator. If S1 and S2 are sentences, then S1 or S2 is a sentence. This is the disjunction operation. Similarly, we have the implies operator. If S1 and S2 are sentences, then S1 implies S2 is a sentence. This is the implication operation. Then we have the if and only if operator. If S1 and S2 are sentences, then S1 if and only if S2 is a sentence. This is biconditional operation. So this is the logic table for all those operations discussed in the previous slide. So if we have P here and Q here, these are the corresponding truth values for P and Q. So not of P will result in negation of P. So if it is false, it will become true and vice versa. So P and Q will result in these two tables, and P or Q will result in this, and so on. So what is a proposition? Proposition is the basic building block of logic, and it can be defined as a declarative sentence which is either true or false, but not both. The area of logic which deals with propositions is called propositional logic. It also includes producing new propositions using existing ones. So propositions constructed using one or more propositions are called compound propositions. Advantages and disadvantages of propositional logic. The advantages are propositional logic is declarative. Pieces of syntax correspond to facts. This implies that every statement in propositional logic is declarative sentence. Next is propositional logic allows for partial or disjunctive or negative information, unlike most data structures and DB. So this wants to say that we can use all the operators that I have discussed in previous slide in propositional logic. Propositional logic is compositional. The meaning of B11 and P12 is derived from the meaning of B11 and P12. So it wants to say that if B11 is true and P12 is true, then only B11 and P12 is true, and thus the meaning of B11 and P12 is derived from the meaning of both B11 and P12 individually. Meaning of propositional logic is context independent, unlike natural language where meaning is dependent on context. So it wants to say that sometimes in natural language, I mean the language that humans speak, the context is dependent, the what we say is directly dependent on the context, I mean, and this is not the case with propositional logic. It is context independent. So what are the disadvantages? Propositional logic has very limited expressive power. Expressive power of propositional logic is very less, which is not the case in natural language. Next, we will see first order predicate logic and calculus. The first order predicate calculus is a formal language. Basic rules for formula in predicate calculus are same as those of propositional calculus. A wide variety of statements are expressed in contrast to propositional calculus. So, first order predicate calculus becomes first order predicate logic if inference rules are added to it. Using inference rules, one can derive new formula using the existing ones. Interpretations of formula in predicate logic is done in the following way. In propositional logic, an interpretation is simply an assignment of truth values to the atoms. In predicate logic, we have variables, so there is more to be done than that. Next, we discuss forward chaining. So suppose we are given this set of predicates from here to here, and we have to prove the first predicate given these predicates are correct. So I'll show you how we will go on in proving this predicate to be true. So the procedure is fire any rule whose premises are satisfied in the knowledge base. add its conclusion to the knowledge base until the query is found. This is forward chaining. So we go from whatever there is in the knowledge base and we move forward by moving to the conclusion of that uh, statement of the knowledge base. So what is forward chaining? Forward chaining is a data-driven method of deriving a particular goal from a given knowledge base and set of inference rules. Inference rules are applied by matching facts to the antecedents of consequence relations in the knowledge base. The application of inference rules results in new knowledge from the consequence of the relations matched, which is then added to the knowledge base. Forward chaining is more like breadth first search. We can also define it as bottom up reasoning. So what it wants to say is we move forward from whatever statements we have in the knowledge base by propagating their conclusions. So for forward chaining, we need to make an AND or graph as shown here. So in an AND or graph, we make the complete representation of our predicate logic from top to bottom, including the predicate we want to prove, that is P implies Q, that is shown here. So implies is shown by a pointing arrow here, and multiple links joined by an arc indicate conjunction. So this is an arc, and this is a line coming out from L. This is a line coming out from M. They are joined by an arc here. So it implies conjunction or the AND operation for which every link must be proved. That implies that L must be true and L must be true, M must be true, I mean, for the AND operation to be resulting in true. Similarly, if it would have been a disjunction or an OR operation, then the any link can be proved. But in this case, we don't need an arc, in which case it would be the disjunction. We don't have the OR operation example here at the moment. I'll show you later. But in that case, any link can be true. I mean, either if it would have been no arc here, either L to be true or M is true, then it would be resulting in true. So proceeding with that example, we'll move forward by making the AND or graph and proving our goal statement, that is P implies Q, from these set of predicates. So here it is written A here and B here. It implies that both A and B are known to be true. So they are marked as red here. Next, what we do is for each arc, we write the number, that is number of lines that are going into that arc initially. So we are marking with 2 2 2 here, and since this is a 1, only P is involved here, we write 1 here. So not necessarily with arcs, we can write it with for every statement, I mean. Next, what we do is for every known uh, line to be true, we reduce that number from the given number for that node. For example, here I have written it as 1 because A is known to be true, so I have reduced that line from the total count. Similarly, A is known to be true here, so this is written as 1 here, again reducing the count from 2 to 1. One more thing I'd like to add, I have written it as 2 here because this is a conjunction. If it would have been a disjunction, I could have simply written 1. So moving in a similar way, since we have this predicate here, A and B implies L, and we know that B is true, so we will subtract one more from here. This will become 0, and similarly from here this will become 1 here. Earlier it was 2 because the line arrow line from here from B is subtracted, and similarly this is 1 here. Earlier it was 2 because A is subtracted from this line. So the line coming out from P here is coming is going to get together with the line coming from A here. So this implies this predicate here, A and P implies L. This line and coming from P, this line coming from L, A implies L. So we have updated the weights now. So since this becomes 0 here, we know that this L here is true, since whenever an arc representing implied condition is has weight 0, which is here, it is known that implying condition is true. So L is now known to be true. So we can reduce the weight for L from this here, and it becomes 0. So now again M becomes known, and we can reduce their weights from here. So now 0 becomes for L and M implies P as well. So P is known now. Finally, since both P and A are known, we can reduce this here to 0. That's not required anyways, but the algorithm will do that. And finally, since P is known, this will become 0 here. Earlier it was 1. So Q is known. Q is true. So we have proven that P implies Q. So we saw how forward chaining works. Let's move on with backward chaining. The idea in backward chaining is to work backwards from the query Q. To prove Q by backward chaining, we have to do the following. Check if Q is known already, or prove by backward chaining all premises of some rule concluding Q. So if Q is proven by concluding rule say A, so we have to prove A first by backward chaining. So the rule for proving A will be similar. We'll use the same logic, that if check if A is known already, or we'll again get some concluding rule for A and try to prove it by backward chaining. So the trick to avoid loops in backward chaining is check if new sub goal is already on the goal stack. So suppose while proving Q, we have sub goal A, and again it comes while proceeding with the algorithm. Then we will discard the backward chaining procedure for A again. So to avoid repeated work, check if new sub goal has already been proved or has already failed. So if you want to avoid repeated work, just keep on checking your stack. If the new subgoal is already proven true, you don't need to go proceed the algorithm for that. Or if it is already failed, then also you don't need to proceed with the backward chaining algorithm for that new subgoal. So backward chaining is a goal-driven method of deriving a goal from a given knowledge base and set of inference rules. It can also be understood as a chaining search system like depth-first search and a top-down approach. So we have seen that forward chaining is a breadth-first search approach and a bottom-up approach, but backward chaining is a top-down approach and a depth-first search approach. So inference rules are applied by matching the goal of the search to the consequence of the relations stored in the knowledge base. In backward chaining, we start from a conclusion, which is the hypothesis we wish to prove, and we aim to show how that conclusion can be reached from the rules and facts in the database. So we start from the thing that is need to be proven and proceed backwards by how by reducing how that conclusion can be reached from the rules and facts that are in the knowledge base. So the conclusion we are aiming to prove is called a goal, and so reasoning in this way is known as goal-driven reasoning. Backward chaining starts with the goal state, which is the set of conditions the agent wishes to achieve in carrying out its plan. It now examines this state and sees what actions could lead to it. For example, if the goal state involves a block being on the table, then one possible action would be to place that block on the table. This action might not be possible from the start state, and so further actions need to be added before this action in order to reach it from the start state. So what it is trying to say here is that goal is the ultimate predicate we want to prove, and reasoning in a backward chaining way is known as goal driven reasoning. We start from the goal and proceed backwards. So the set of conditions which will make this goal to be achieved are favorable for our algorithm, and that will be pushed onto the stack for further processing for the algorithm. So we will move on with the backward chaining examples, the similar example, but in this we'll start first with the goal statement of P implies Q. So first we'll assume Q is true because we want to prove that Q is true when P is true. So we assume Q is true, and here already A and B are known statements from here and here. These are true statements. So by backward chaining, since Q is true, we'll proceed backwards from here to here, and this will imply we'll take P to be true, assume P to be true in fact, and proceed with backward chaining algorithm again. Next is, since P is true, we'll take this predicate from here and put L and M to be true. Here L and M will be true. Now since P is true and L is true, uh, we can take this predicate here and push A onto the stack. But since A is already known, uh, uh, we'll move on with the next step of the algorithm. So now, since M is known to be true, or assumed to be true in fact, so we'll take this predicate here, and so L is already known, but we'll push B onto the stack of known to be true variable. But since B is already true, we move on to the next step of the algorithm. So now A and B are known to be true and are true in fact. So our assumption that L here is true in the backward chaining algorithm step was correct, and we can mark it as known to be true. Now we'll take this predicate here and since B and L are now known to be true, so M will be known to be true now, and our assumption that M was true was correct. Next we will take this predicate and moving backwards P will be pushed onto the stack and it will be a known variable. Next P is in the set of the known to be true variables, and since our original assumption was Q is true only if P is true, we will next move Q to the set of the known to be true variable set. So finally we have Q is true, then our assumption that uh, P implies Q is true, which is the goal. So we have proven P implies Q by backward chaining. Forward chaining versus backward chaining. So forward chaining is data driven. So we have a lot of data and we need to prove a goal from the data moving forward from whatever we have in the knowledge base. So forward chaining is automated and unconscious processing because forward chaining is a simple algorithm, and example of forward chaining is object recognition and routine decisions. So routine decisions for a business entity and object recognition implies, for example, handwriting recognition. So this may imply forward chaining, and forward chaining may do lots of work that is irrelevant to the goal. So as we have seen in our forward chaining example, the last step was not necessary at that point of time. Uh, Forward chaining may do lots of work that is not required for the goal achievement. So next we have backward chaining. Backward chaining is goal driven. Where we have seen in forward chaining that forward chaining is data driven, backward chaining is goal driven. We start from the goal and proceed backwards to facts. So backward chaining is appropriate for problem solving. So it wants to say that suppose we have a problem, we can move backwards to the facts that help us in solving that problem. For example, where are my keys or how do I start the car? These both problems require facts, and moving to those facts can solve the problem. So the complexity of backward chaining can be much less than linear. So what it is saying that uh, the complexity or working on time complexity of backward chaining can be much less than linear or polynomial time. So if you know the complexity classes of polynomial or linear, it will be clear. So backward chaining is very lesser than polynomial or linear time.